So our first speaker is Amy Pang, and she's going to talk about monomial bases for combinatorial Hopf algebras.
Thank you, Laura. And thank you to all the organizers for having me and for running such a great conference. So today I'm going to talk about a project with Nanta, Rafa, Shrushal, and Yannick, and our upcoming paper is called Hopf Algebras of Parking Functions and Decorated Planar Trees. And in it, we define these two Hopf algebras, but the part that more, excites me is that we build monomial bases for them, and in a way that also works for a lot of other Hopf algebras. Okay, so what do I mean by monomial basis? Maybe I should demonstrate its properties with a well-known example of quasi-symmetric functions. So this is the monomial quasi-symmetric function, and it's indexed by compositions, which is like a list of positive integers. But I'm going to represent these as diagrams. So here, the colors in the diagrams are not part of the diagram data. They are there to help illustrate things. Okay, so they're like working like highlighting. So how you can tell that this is 2, 1, 2 is you look at where I draw a black line. Okay, there's things I call divisions. So there's a division after 2 squares, and there's another division after 1, and then there's 2 more. Okay? And so what is M212? It's a power series. So with terms like xi squared, xj, xk squared. And so here are some of the terms that are in this power series. And I'm going to use the word degree of a composition to mean the number of squares. So this example is in degree 5. Okay, so let's look at the product in the monomial basis, and actually the exact formula is not going to be important. Okay, the important thing is that it expands positively, meaning if you take a product of monomials, then you get a sum of monomials. So if you expand it in this basis, all the coefficients are positive integers. That means that I can visualize this product as there is a rule for combining these composition diagrams, right? So I have this diagram, and then the rule here is that I can put the yellow block anywhere like in between the blocks of this green and red thing. Okay? And you see some, and when on the left of the yellow block, I can either have a division or I can not have a division. So if you think through all the possibilities following those rules, and then you take the monomial basis elements corresponding to that and add that up, that's your product. Okay, so for me, a product is describing what are the possible legal ways of combining two of these composition diagrams. Okay, so as I said, the exact rule is not very important, but I can run through that quickly anyway. So you want to multiply xi, xj squared with xk. And so you think about what k can be relative to I and j. So k can be bigger than I and j. And that would mean that this yellow square goes at the end of the green and the red. Or k can be equal to j. So then the red and the yellow will merge and become a single block. And that's why this gives you a block of size 3. Or you can put k in between I and j, and then this yellow block will go in between the green and the red. And if k is equal to I, then the green and yellow will merge, and that's why these are the 5 possibilities that happen. Okay, so that's the products, but I'm more interested actually in the co-product. So QSIM is a Hopf algebra, meaning that in addition to the product, there is a compatible operation called the co-product. that you can think of as I have a composition diagram. I'm going to the output of the coproduct is going to be the sum of all legal ways of breaking up this diagram. So I start with one diagram and I break it into two separate diagrams. Okay, and again, the exact rule is not going to be so important, but at the end I'll point out what are the important features about this particular rule. Right, so I'm going to go. I'm going through how to do it, but somehow that's less important. So you have your power series, which is in the x variables. Now substitute into it the y variables followed by the z variables. So for example, I could say this. I can make this first one into a y, and then the other two into z's. Okay, and so it would look like this. Okay? And then we still have that j has to be less than k, but because all the y's appear before all the z's, I don't actually have to specify how I is related to j and k. I can be anything now. And so now I look at this, I look at just the y's, and I think about what is the quasi-symmetric function that the y's represent. So when you have terms like this, it's going to give me an m1. And then the z's, right, because there's a zj squared zk and j is less than k, this gives me an m21. And so that's what I write down here. Okay, so that's one of the possibilities, that the first is a y and the others are z. There are some other ones, like I can make the first two into y's and then the last one can become a z. So then that gives me m12 and m1 as the things in the coproduct. And then the x's can all be z's or the x's can all be y's, but I'm not going to care about those cases because I'm looking at the coproduct with a plus, which means that I remove the 1 tensor f and the f tensor 1 terms. Okay. So again, like what happens with the variables is less important. Like think about in terms of the diagram. The rule for the diagram is that we can deconcatenate between the blocks. So anywhere between two blocks, you can split it, and then I can split into the green on the left side, and then there'll be the red and the yellow on the right side, or I can split it after the red. So what's special about this coproduct is that it is representing some sort of unique factorization. You can think of this as being the 3 blocks as being the 3 factors of this composition. Okay, and what the coproduct does is that it's basically deconcatenating between the factors. This is the essential feature of the coproduct of a monomial basis. This is called a co-free coproduct. So when I'm saying I want a monomial basis for other Hopf algebras, what I'm saying is, so in another Hopf algebra, the basis elements are going to be indexed by some other type of diagram or some other combinatorial object. And I want to see a unique factorization in those combinatorial objects and have a coproduct where it just deconcatenates between the factors. So this is really important, this idea. So I just want to have everyone think about this for a few seconds. Okay. Okay. So the same Hopf algebra can have many different bases. Okay, and even though the products and the coproducts in the linear algebra is the same because you're in the same Hopf algebra, when you express these rules in terms of the combinatorics, they will look different. Right, like in the monomial basis, you see a combining rule given by quasi-shuffle of blocks, and a breaking rule given by the deconcatenation between blocks. But if you chose a different basis, right, then assuming that it has a product and co-product that still expands positively, you're going to see a different rule for a different rule for combining those composition diagrams and for breaking up the composition diagrams. And the idea is that by using different pairs of rules, different perspectives come into light, right? As I was saying, if you use the monomial basis where you have this free co-product, then you see unique factorization. So this is why we're interested in changing between the different bases, because they're still in the same Hopf algebra. So their bases are also related to each other. So that helps you study the different aspects. So I can look at the fundamental basis, for example, which I'm going to define using a poset. So this is a poset by refinement. So what happens here is that every cover relation is you add a division. You add a black line somewhere in the diagram. And if you want to calculate what is F31, then you find 3,1 in this diagram, and you look at what is above it in the partial order, meaning what you can obtain by adding extra divisions to 3,1, and you just add up all those monomials. Okay. This is the equation is also going to be very important because I'm going to make my monomial basis elements out of fundamental basis elements. So QSIM is actually a bit unusual in that the first basis we think of is the monomial basis. This is really rare for other Hopf algebras. It's more likely that like the first basis you think of is more like a fundamental basis. And by like a fundamental basis, I'm going to explain the product and co-product that I expect that like justifies why I call them a fundamental basis. So because of time, I can't actually explain why this is the rule, but the product rule for the fundamental basis is the shuffling of squares. Okay, so here I'm shuffling the yellow square into any position between the green and red squares. And this is not based on blocks. So that's why the yellow square can go in between the two red squares. Okay. And just to demonstrate what the shuffle means is another example. So here I'm shuffling two squares with two squares. And the 6 outputs that you see here are all the ways to have a green before red. Okay, and also in the second input, the squares have to have the same order. So you have a yellow in front of a yellow. Okay, and so that means crucially that the number of terms you see is only dependent on the degrees of the inputs. Right, like the number of, so this is entirely different from the monomial basis case where there's something to do with like how many blocks there are. This, like the number of terms does not see how many blocks there are. Okay, like I could put this as a 1, 1 or something and it would still create like these 6 strings. So that's the important part. The quick other thing to say is that whenever if I have a block from the left input and then a block from the right input, then there is never a division. But if it's the other way around, like I have like a block from the right followed by a block from the left, then there's always a division. Okay, but that's sort of just a. And then in the co-product, there's a similar sort of independenceness. The co-product turns out to be deconcatenation between squares. And it will always produce one term in each degree. Okay, so again, this is square-based. So I can cut after just one green square in the middle of the green block. And this gives me a 1 and a 2, 1. Okay. And so if I cut off the 2 squares, it gives me degree 2 and degree 2. And then I can cut off the 3 squares. It gives me degree 3 and degree 1. And this will always be true no matter what composition I have here. I will always get 1 term in each degree. So this coproduct is not based upon any sort of unique factorization idea. So if you remember, maybe I'll just, so in the coproducts for the monomials, if I gave you one of the terms in the output, you can know where it came from because this has all the factors in it, and then you just put the factors on this side and this side together. Right, but this is not true when you allow deconcatenation in the middle of blocks, because if I told you that this is the output, you can't tell in the input whether there used to be a division between these 2 parts or not. So that's why this is not saying anything to do with unique factorization. Everything okay so far? You guys should, yeah, if you want to ask something, feel free to like write in the chat. I can look at the chat, and also my coworkers are around if people want to ask things. Okay, so the idea is that in one of the common combinatorial Hopf algebras, you have a basis that acts like the fundamental basis, in the sense that the product is given by some sort of shuffling, and the number of terms is always like a binomial, right? It's the degree of the output choose the degree of one of the inputs. Okay, and then you have a coproduct that is some sort of deconcatenation, and it produces 1 term in each degree. So in the next slide, I'm going to give an example of what shuffling and deconcatenation might look like for some other types of combinatorial objects. And a lot of people in their Hopf algebras have defined a poset on the combinatorial objects, and then defined a monomial basis using that poset in the familiar relationship between fundamentals and monomials. Okay, I mean, we said that this defines a fundamental as a sum of monomials, but you can do Mobius inversion on this formula because it's a triangular formula, and so that will give you that will allow you to inductively define what the monomials are in terms of the fundamentals. And then they prove, okay, all these various people and even more in their various different Hopf algebras, they prove that the coproduct in this monomial basis is cove-free. So that means they actually find what is the unique factorization of those combinatorial objects. And there are some common elements to all these proofs, but somehow each proof is sort of written from scratch again. And a lot of the ideas are being repeated across the different proofs, and that's sort of not very satisfactory for me. And also, not all of those people explored what the product is for the monomial basis. So in many cases, we don't even know whether the product is positive or not. So to address these issues, one of the more complete studies of monomial bases is by Aguirre and Sottili, and this is on the Hopf algebra of permutations. So what we did is that we made a list of axioms for an arbitrary combinatorial Hopf algebra, under which the Aguirre-Sottili proof is going to go through. Okay, so the axioms are things like that the shuffle that defines your product, and the deconcatenation that defines the coproduct, and the poset, these have to interact in some specified way. Okay, so now instead of you have new Hopf algebra, prove that its monomial basis has these properties. Instead of having to do that again each time you have a new algebra, now you just check all these conditions, and then our theorem will tell you that there's a co-frequent product in the monomial basis. And also we have a formula for the products, and it turns out to be positive. So let me show you those theorems. And my example is going to be one of the new Hopf algebras that we made on parking functions, which we view as a tree whose internal nodes are labeled with a permutation. There are some conditions which, for reasons of time, I'm not going to explain in detail. You can chase me or my co-authors afterwards and ask how it works. Okay, and so the first axiom is that the co-product has to be what I call deconcatenate everywhere. So let me explain why what's written here is deconcatenation. So this line here on top of the formula, I'm trying to explain why the co-product comes from a deconcatenation, because it's like, if you think about what I want to think about, splitting the tree down that red line. Okay, so if you know Lode-Ronco, this is Lode-Ronco operations, and just standardize the labels. Okay, so people who know Hopf algebras is what you think it is. People who don't know, maybe I can still convince you that what's happening here is that this tree on 3 vertices is really this part that is on the right of the red line, and this tree here is this part that is on the left of the red line. Okay, and I cut, and the red line, it starts at any of the leaves that are not the outermost ones. So this one, I start now at the next vertex, and you can see that this part is the left side of the red line, and this part is the right side of the red line. So that's that. I know I'm not explaining all the details, but hopefully this gives some idea of how deconcatenation works for other types of combinatorial objects. And this is my notation for deconcatenation, so that the left piece has size I. So for example, if this is F, if this tree is called little f, then this would be called 1f, and this would be called f1, and this would be like 2f, because this is so the degree here is the number of internal nodes. So this would be like this, sorry, because I'm saying that this part is the part that has a degree high. Okay, actually, I can relax this condition a little bit. It doesn't have to be deconcatenate everywhere. But again, I don't want to explain that because I want to keep things sort of simple. Okay. So that's the first axiom. And then, well, that's clearly not enough because I need to know something about the order, about my posets and how this works, right? So the second axiom is that the deconcatenation is order preserving, meaning if f is less than f prime, then after the deconcatenation, the inequality is still true for both parts of the cut. Okay, and the order on the parking trees is okay. Again, I don't want to go into detail on this, but it's some combination of Tamari and weak order. It's very nice. Okay, so there's one more axiom, and before I show you that one, let me show you the theorem so you can understand why we need the third one. Okay, so if the theorems are all satisfied and we define a monomial basis by the usual way, then I want to say that the co-products in monomials is still deconcatenation, right? Still like this IFFI. But the difference is in the sum, right? I'm no longer summing, like here I summed from I equals 1 to, I summed everywhere, right? Deconcatenate everywhere. And in this one, I don't just sum over some subset of i's because I want deconcatenate between blocks. Remember, I want to have a unique factorization and be deconcatenating between the factors. So the third axiom is, how do I tell what is a block in one of these combinatorial objects. Okay, so this is how we do it. So first, the crucial idea is maximal concatenation. Okay, so let me explain what it is using this example with the compositions. So this, so if I give you two compositions, then I can think of the set of concatenations of them. Okay, so for compositions, there are only two. And what I mean by a concatenation is that it's a composition whose deconcatenation gives you the two pieces, right? So if you do whatever defines your co-product in the fundamental basis, do this to your objects, and then it results in these two pieces. So here there are only two possibilities because the only thing you can decide is whether you have a division at in between the two parts or not, right? You can divide there or you can not divide there. Because what happens in all the other parts, you can tell where all the other divisions are because from the two pieces. Okay, now which one of these is maximal? Remember that a additional division is a cover relation. So you want the one that has a division there. Okay, so what is this? So this is I write the slash for this maximal concatenation. So what this means is that how you can tell, like one way to define a division is that it's where if you cut it and then make a maximal concatenation, you get back to what you started. Okay, so that's the definition, right? If you cut it into IF and FI, and then you take maximal concatenation, you get back F. So the positions of maximal concatenation is what we define to be, so we call them global descents after Aguirre-Sottili on, because they're working with permutations, that's what they're called there. And so for this example, I can tell you that the only global descent is there. So these two are the only factors. I cut here, right? Then these two are the only factors in the unique factorization of this tree, and that's why this is the co-product if you use the monomial. But I don't have enough time to explain what it is clearly because I didn't explain how the poset works completely. Okay, there's a question of is the parking order new? I believe so. I don't know. Maybe like Shu Xiao can help me. Okay, so just real quick, I just want to show you what the product axiom looks like. So you need the product to be a sum of shuffles, and you can understand this by that if I have a degree 2 and a degree 2, then it will create 4 choose 2 terms, and hopefully from the diagrams it looks like the yellow thing is shuffling into the green thing, and it's loaded wrong code with shifted labels, if you know what that means. And shuffles have to be order preserving and also join preserving. And if this is all satisfied, then the coefficients in the product is the number of shuffles satisfying some unsightly formula. I don't actually know how to calculate this, but at least we know that it's positive. So I just want to say why are we doing this? Okay, like what exciting things can we do with this? So I've been saying, you know, it allows us to see the unique factorization of a combinatorial object. So that so not every combinatorial object is going to have this unique factorization because not every Hopf algebra is code-free. So if your Hopf algebra is not code-free, then that means there's no basis that satisfies those axioms that I showed. So that's cool, but something that's more cool is that you can use this to make isomorphisms. So Yannick made a self-duality isomorphism from, so what he does is on WQSim, make some monomial basis, make one for the dual ortho, check that the unique factorization in the two monomial bases are the same, and then look at this formula and show that this formula is also the same for the two Hopf algebras, and so you have an isomorphism. So that's super nice, and I would really like to use that to make an isomorphism between our new parking tree algebra and the parking functions Hopf algebra of Novelli and Thibon, because we know from an abstract theorem that they should be isomorphic, but we don't know an actual explicit map. So if we can make a monomial basis in PQSim and then check that they match, then we would have an isomorphism. Okay, so I'm gonna stop there, and you can chase me down if you want to know the various details for this.
Okay, so let's turn Amy. So there was one more question on the chat. I don't know if you can read it.
Yeah. Oh,
and
does
Yannick,
it, Yannick? Is that true? Okay, I don't know. I mean, yeah. Okay. So I'm not sure about the specifics of this. Yeah.
Okay, so maybe Yannick and Dorian, you can talk at some point during the gather town or just by private chat. Is there any other question?
Maybe while we're waiting, I'll just add another comment, which is that actually the co-product, proving that the co-product is co-free is not too bad in all the different cases. So that's why people have been doing it separately. The bad thing is the product thing. Like the proof of this is like, I think I wrote something like 4 pages. So this is why like checking streamings does not take 4 pages. This is where you actually like save a lot of time. This was the product is what motivated us to do this. Like we were happy to just do the co-product separately for all the algebras. The product and also the antipode. We also have cancellation-free formula for the antipode. Again, just what Aguirre-Sottili says. And this, the proof of this is like, oh my God, it's even more than 4 pages.
Okay, that's really nice. I was going to ask about the cancellation-free formula. So any question?
It's very bad inclusion-exclusion. But it's basically Aguirre-Sottili.
Okay. Okay, so there are some more comments that you can check out on
thank you,
on the
guys.
chat. So I think like we are gonna thank Amy again and just continue the conversation on the chat.